You know, I get asked all the time, why do you study meteorology? Well, I'll tell you something. When I was younger, there were a lot of major weather events that I got to witness live because of the advent of this thing called the Weather Channel, where I could watch 24 hours a day all of the most severe weather on Earth. And I'll tell you, this one event that I just paused this animation, this satellite animation to show you, was one of the big ones for me. I was 13 years old, and it was March 1993. And we're going to watch here the evolution of the Superstorm of 1993. Now, what was amazing was this kind of marked the beginning of our ability to do some great both short-term and long-term forecasting of powerful winter storm systems like the one that you see right here. And I'm telling you, this one did it all. It produced a massive squall line of thunderstorms that raced through parts of Florida, producing storm surge, not from a hurricane, but from squall line winds that inundated the west coast of Florida. It produced hail, it produced tornadoes, it produced a flood, it produced a massive ice storm, and a blizzard, all of it. In addition to all of that, produced incredibly strong winds around this entire really deep low pressure system. Well, I watched it from start to finish, and I was fascinated. I was just fascinated that our planet and its atmosphere can, at any given time, produce such violent expressions of weather. Well, this is what we're going to be learning about. Massive low pressure systems just like this one. And where did this one start? If I take you back here, right on the boundary between the warm water in the Gulf of Mexico and the land here in North America, right there in the Gulf. And check it out, there it goes. Now, we know why big low pressure systems spin. It's due to the Coriolis force. And as this one went racing up the northeastern part of the United States, it created what we call a nor'easter. That's just a nickname we give these big, powerful storm systems that go up the northeast part of the United States. It's neat. Do you actually see how there's clear air right here, just along the coast, and then streets of clouds that form after that? That's actually a telltale sign that bitterly cold air is sweeping off the continent onto the ocean here. It's incredible to be able to see that. Well, when this storm system went through, it caused a lot of damage. And the animation here is going to zoom in on all the snow that fell from Mississippi and Alabama up into parts of the Carolinas, Tennessee, Kentucky, West Virginia, Ohio, Pennsylvania, New York. Look at all the states it hit as it went up the East Coast. When it was all said and done, they said if you would have taken all of the snow and melted it and made basically liquid water out of it, and piled it on top of New York, it would have flooded the state of New York in 2 feet of water. Now, I remember one other very interesting thing about this storm system, and that was right along the northeast quarter. Now, you got to remember something. You know, there's something that I just kind of circled in here. Maybe 100 million people or more live right inside that circle. Well, as the low pressure system tracked up the coast just like this, and all the snow fell on the backside here, the blizzard was crippling. And what was interesting was it turned out that this particular storm system sent a whole bunch of pregnant women into labor. And there was a big study that broke out because of this, because they were wondering, well, was it the incredibly deep low air pressure that basically changed the physiology of the women that were pregnant and basically sent them into labor? Or did it have to do with, you know, psychology? Were they worried? Were they thinking that this was, if they didn't get to the hospital, well, the blizzard was going to shut everything down, it was going to cause problems? And it was a very neat study because it kind of turned out that they were, well, thinking a little bit about both sides of the story there. But it turns out, when we kind of look at it in the longer term, that more than likely what caused so many women to go into kind of premature labor here was anxiety. When this storm system went through, it cleared out every single shelf in every single, let's just watch this again while I'm talking about, every single shelf in every single supermarket. Because watch, as storm systems like this blow up and hit this part of the United States, again, more than 100 million people in 1993 were hit here. Modern day, we're talking closer to 200 million people would have been impacted by this. You know, when these things happen, well, people panic. They worry because the blizzard, well, I'll be honest with you, the blizzard is a formidable beast. In other words, it actually behaves much more like a military foe. It blinds you. It locks you in. It cuts off your communication. That's exactly what militaries do to overtake an area. It's just impressive to see a blizzard like this one do this. So this is what we're going to study. Winter storms that make blizzards and ice storms and all sorts of cold air outbreaks and stuff like that. This video lecture is a primer. We're going to go through and just try to understand the very basics about what we need to know to understand how these systems form and where they go. So let's get started off with another satellite image here. Just to be clear here, I call this an extratropical cyclone. Extratropical. Outside of the tropics. That's what that means, outside of the tropics. It's still a cyclone because the thing spins like this counterclockwise, so it wraps in just like that. Just like this tropical cyclone is spinning just like this. Now, just so you know, extratropical cyclones are much, much, much larger than tropical cyclones. Look at what I just drew for you here. It starts in Texas, actually in Mexico, races through the lower Mississippi River Valley, into Ohio, over the Great Lakes, way up near the Hudson Bay, wraps back around to Minnesota, Wisconsin, through the Great Lakes. This is a huge storm system. Whereas a big hurricane, which is something you see over here, may only occupy 1 or 2 states. So the extratropical cyclone, again, that means it's outside of the tropics, is a large, powerful storm system, and it can produce everything. We can get blizzards, ice storms, flooding, all types of severe weather like supercells, squall lines, hailstorms, tornadoes, all of it. And if they don't happen, if we don't get extratropical cyclones, we have drought. So that's it. This is a very, very important part of mid-latitude weather. And again, mid-latitudes, that's right here where the United States sits. So that's our setup. Okay. We get into the next part here. Let's talk about the characteristics of it. So I got 3 different graphics here. And I'll tell you, the big take-home points on this slide are what you're going to see down here on the radar image. Let's get some of the basics out of the way. Remember that these storm systems spin in a counterclockwise direction. So if I kind of put a little arrow in here to kind of show you how they spin, they wrap around just like that. Because they do that, they form this comma shape in a cloud field. So actually we call the cloud field around an extratropical cyclone the comma-shaped cloud field. Looks like the punctuation mark comma. And that's because in the backside of this 1,000-mile-long cloud system, you have something called a dry slot. See it right there? And this is where some drier air from the desert southwest, some drier air from the upper levels of the atmosphere, kind of converges and sweeps right into the backside of the storm system, punching this hole into it. That's a major difference between the extratropical cyclone and the tropical cyclone. Tropical cyclones don't typically have these large defined dry slots. That's why the extratropical cyclone has this counterclockwise rotation that looks like a comma. Now, where I live right now is right here. I live near Champaign, Urbana, right where that X is. And there's always a running joke around here. Oh, you don't like the weather? Well, just wait until tomorrow. Why do we have such incredibly volatile weather right here in the middle part of the United States? Well, that map over on the right kind of gives you an idea about this. What you see labeled and color-coded here are all of the different types of air masses that surround the United States. Now, what's an air mass? It's just a large blob of air that has similar moisture and temperature characteristics. Now, you don't need to memorize all the different types here, but basically, we have some from the north that are cold and then really cold. We have some to our northwest and northeast, which are over the ocean, so they're cooler, but they're moist. We have one that comes right out of our desert. We call that a continental tropical. That's hot and dry. And then we have a lot of what we call maritime tropical air masses, those being hot and humid that come from the Atlantic, the Gulf, and the south, kind of western side of the United States over by the Pacific. Now, why I'm pointing all of this out is all these air masses basically move in that direction. And you can see where the arrows point. That's why we have such incredible variety of weather right here in the central part of the United States, in the mid-latitudes. And it's the low-pressure system that spins them all up and mashes them together. And every time they hit, when 2 air masses collide, you get a front. And fronts are focal points for weather because the air is forced to rise where it collides. So that's what a front is. When cold, dry air meets warm, moist air, or cold, dry air meets hot, dry air, all of it, that's what we're talking about. Now, again, here's the take-home point. When these air masses are blended all together by the rotation, the counterclockwise rotation around a low, you get all sorts of different types of precipitation. And if it's late fall, winter, or early spring, again, late fall, winter, or early spring, that's our cold season in the middle part of the country, we tend to get low pressure systems that produce this variety of precipitation. So pay close attention. To the south of the low, there are thunderstorms. See it labeled down there in the bottom? To the east of the low, there's often rain. To the northeast, there's freezing rain, sleet, and on the backside, snow. Now, we've already talked about the rain and the thunderstorms, but right here is where the low is typically situated. And what we want to study is the types of weather that are to the north and northeast of the low. The snow, the sleet, and the freezing rain. So basically every deep low pressure system like this in late fall, winter, and early spring has severe storms to its south, rain to its east. That rain transitions to freezing rain, sleet, and snow. We've got lectures coming up on snow, sleet, and freezing rain, so that's all coming ahead. But that's the main idea behind the structure of one of these storm systems. All right, let's get a little bit of review in here. We know a few things. We know that the air spirals around a low pressure system in a counterclockwise direction. That's what you see right up here. See the air spiraling around counterclockwise? The red arrows represent warm air. The blue arrows represent cool air. And you can see where those air masses collide. we get a cold front, where the cold air is advancing toward the warm air, and where the warm air is pushing into the cold air, you get a warm front. And that's just the collision of these large air masses I've labeled around here. But this class is not about really the Meteorology 101. It's more about the severe aspect. In other words, in 10 years from now, I want you to be able to watch the Weather Channel or watch your local news broadcast and listen to a meteorologist discuss the track and the evolution of a low pressure system, and then you remember what to expect where. So just like with tropical cyclones, extratropical cyclones have very characteristic precipitation types at certain spots around the low. So let's get some practice. Now, this is just a review of what I just taught you. Look at that map in the upper right-hand corner. Question: what type of weather do you think happens where I just highlighted? See it up there? Where I'm highlighting this blue blob, okay? You're to the northwest of the low. Now, what I want you to do is help me match up the weather symbol, and I have not taught you weather symbols. But when we design these weather symbols, they're supposed to look like the weather that we would have. So one of them represents thunderstorms, one of them represents rain, one of them represents sleet, one of them represents snow, one of them represents freezing rain. What type of weather do you think happens to the north and west of the low pressure system that's way back here in the cold air? Think about it for a second. Got an answer? Well, hopefully you're all thinking about snow. And that's the symbol we use for snow. That's the heavy snow symbol, 4 stars or 4 asterisks. All right, let's keep going now that you've got an idea about this. We're just north of the warm front now. See the little blob I put there? Just north of the warm front. And when you're just north of the warm front, you're in this cool, moist air. So we know there's plenty of moisture to make precipitation, but the cool means it's temperatures below freezing. So we're not going to be getting rain there. We're certainly not going to be getting thunderstorms there in winter. We're either going to be getting sleet or freezing rain. Now, do you remember the transition? Okay, the transition first goes just north of the warm front to freezing rain and then to sleet. The question is, which one of these symbols is the freezing rain symbol? Because that's what would happen right here. Think about it. Got an idea? Well, it's that one. I know it's kind of strange. It looks like a yin-yang symbol, but that's what it is. What about right here? You're now deep into the warm sector. So we know we're not talking here about sleet or snow or anything like that, where the temperatures are above freezing. What type of weather did we get just east of the low? Do you remember that from a few moments ago? Well, hopefully you're thinking about rain. And our rain symbol looks like our snow symbol, but instead of asterisks for snow, we have dots for rain. So heavy rainfall is 4 dots, just like that. Next, what do we get down here? This is to the south of the low, along the cold front, near the Gulf of Mexico. Well, down here we get thunderstorms. And our thunderstorm symbol is this symbol right here. And it's supposed to look like a thunderstorm. So look at it. This is the updraft. That's the anvil, that crossbar across the top. And you guessed it, that is lightning. And that's the type of weather that belongs down here to the south. And finally, what kind of weather do we get here north of our freezing rain band? We will get sleet. And sleet looks like a triangle with a dot in it. So again, thunderstorms, rain, freezing rain, sleet, snow. That's the transition of precipitation types around an extratropical cyclone. Now, before the Weather Channel began to name their winter storms, and they have a great big long name list of everything they call these now. They just make up a new one every single year. Meteorologists would basically identify low pressure systems and their tracks by the location where they formed. So one of them is called an arc-latex low. And my question for you is, which one of these 5 tracks, do you see, or A, B, C, D, or E, do you think is the arc-latex low? Now think about it for a second. Okay, got an idea? Well, the answer to this one is C. Now, let me help you name these. First, all of our low-pressure systems in the United States are reinvigorated. They're re-energized, or they begin right after they cross over the Continental Divide, over the Rocky Mountains. So we name our low-pressure systems after where they start. Now, this is different from the convention that the Weather Channel uses. They just put names on them so they're easy to identify, so they can talk about, Winter Storm Thor or something like that. No, we don't do that in atmospheric sciences. We talk about them based upon their tracks. A is an Alberta Clipper, starts in Alberta. B, Colorado Low, starts in Colorado. C, Arc-latex Low, Arkansas, Louisiana, Texas. D, the Gulf Low, and E, the Hatteras Low, all of them named after where they start. Now, this is not the only location in which low-pressure systems can start, but these are the most common. One of my favorites is called the Panhandle Hooker, okay? It happens somewhere between the Colorado Low and the Arklatex Low, somewhere right in there on the panhandles of Oklahoma and Texas. And it hooks to the south first and then goes on off to the northeast just like this. So it gets its name, the Panhandle Hooker. Just kind of a fun name which we assign to that track of a low-pressure system. But as we discussed when we talked about tropical cyclones, track is everything. You need to know where you are with respect to the cyclone track, with respect to the extratropical cyclone track, okay? So let's talk about those tracks first. How long does it take for one of these extratropical cyclones to move across the country? Typically 2 to 5 days. And as you can see here from their blue arrows, that they mostly move from the southwest to the northeast. All right, names. Alberta Clipper, okay? How does it get its name? Well, it moves very, very quickly along the U.S.-Canadian border. So the Clipper in Alberta Clipper means that it moves quickly. I've seen some Alberta Clippers go from Alberta, Canada, all the way to Maine in a day and a half. You can't even drive it that fast. So they move quickly. Now, why we care so much about them? Well, when an Alberta Clipper comes racing out of Alberta, Canada, on the backside it brings in incredibly, incredibly cold air and some of the worst blizzard conditions on the planet in the northern plains. And we're definitely going to talk about that very soon. Colorado Low. The Colorado Low typically starts right here in Colorado and goes racing toward, well, about the Chicagoland area before it goes off to the northeast. Now, why I've highlighted this is because I teach out of the University of Illinois. Now look, the Colorado Low goes to the north of Champaign-Urbana, which is here, which means we're on the south side of the track of the low. Therefore, we get rain. So when one of these things happens in winter, Chicago gets snow, we get rain, all right? But my absolute favorite low-pressure system is the Arklatex Low. And the reason why? We get snow at the University of Illinois. You see, the Arklatex Low sometimes starts here and goes right up through Tennessee, Kentucky. Sometimes it'll go through southern Illinois and Kentucky, Indiana, Ohio. But anyway, when this low-pressure system goes to our south, we're in the cold air. We're in the location where we get the heavy snow. And why I love this one so much was back in February of 2013, we had, on the day that I was going to be teaching about blizzards to my class at the U of I, we were having one. I didn't go to sleep the night before. I stayed up all night and watched the snowfall. By the time it was about 6 o'clock in the morning, we had already had a foot of snow. But for some reason, the university didn't cancel classes. But I was excited. I was going to go teach kids about blizzards on a day we were having one. So I got in my car, raced off to school. I usually have about a 5-minute commute to get to school, at least where I used to live. It took me an hour, but I got there. And when I got there about 8:30, everybody got an email from the chancellor saying that classes had been canceled. It was too treacherous to bring people into the university. Now, by the way, for my students at the U of I, we will cancel classes based on weather if the weather is really bad, especially in winter. And I'll tell you this, if you want classes canceled because of winter weather, it needs to be bad enough that the faculty and the staff can't get to work. That's what they really base it upon. Oh, but by the way, you're in college. You can take a snow day any day you want, right? You can take a snow day when it's sunny and 80 degrees. That's the beauty of college. Well, anyways, let's get back to this. The track of the low. Why I loved this one so much was by the time I got to school, we had 13 inches of snow. Chancellor cancels classes, and I'm totally bummed because I'm basically the only one that bothered to go to work that day, and I can't get home. My car's blocked by the snow in the parking lot. Then, right before my 11 o'clock class, I get a phone call. It's 10:30, and I will never, ever forget this. The phone rings, and I pick it up, and it's the Champaign County Jail. And they asked me if I want to take a phone call from John so-and-so. I won't mention his last name. Well, I said, well, sure. I've never been called from the jail before. I've got nothing better to do. I can't teach today. So I took the phone call, and the operator clicked me over and said, you're on with Professor Snodgrass to John on the other end of the line. And he goes, Professor Snodgrass. And I said, yeah. He goes, I'm in jail. And I said, I kind of got that idea, what's up? And he goes, well, I'm in jail. And at this moment, I'm thinking, shoot, he's going to want me to bail him out. I said, well, tell me what happened. He says, well, last night, remember when all the snow was starting to fall that you told us about last week? I said, yeah. He says, well, a bunch of us were going out to Schnucks to get a bunch of food. And when we got there, there was a huge snowball fight in the Schnucks parking lot. So we kind of joined in. He says, I said, okay. And he said, then all of a sudden, that snowball fight turned into a fist fight, and everybody was fighting. I said, were you fighting? And he said, no. He goes, but I still got thrown into jail. And I said, all right. And I said, well, is somebody getting you out of jail? He's like, no. And I said, why not? He goes, my dad called all of my friends and family and told them not to bail me out. And I said, why? He goes, well, he thinks I was in the fight and he thinks I should stay in jail to learn my lesson about this. And I said, were you fighting? He said, no. And I said, okay. And then I said, well, why did you call me? Now remember, my class was going to start in about 15 minutes, all right, even though it was canceled. And he says, well, I was just wondering if I could still get iClicker points for today. And I started laughing so hard. I said, John, you've got bigger fish to fry. This is most definitely an excused absence. And he was so relieved over this. So I hung up the phone and I sat there for a moment, kind of absorbing what had just happened. I'll be honest with you. My head inflated to the size of my room. I was so pleased because, and this is what, my vision of going to jail is you get one phone call, right? And I was John's one phone call to tell me that he wasn't going to be at the class and that he would like to have the 10 points that he would get from iClickers. And so that maybe been the moment that I started to think that students may actually like my class. Anyways, Arklatex low, back to it. Snow on the northwest side. Now, that big nor'easter I showed you a few moments ago, the massive cyclone called the Storm of the Century, that one began as a Gulf flow and then went right up the east coast of the United States. So often a Gulf flow will transition into a Hatteras low or a nor'easter. And remember, nor'easters are powerful because they race right up here along the boundary of the warm ocean current from the Gulf Stream and the cold, cold air over land, producing powerful, powerful low-pressure systems. And hundreds of millions of people are impacted. So that's it. These are the tracks I want you to know. Alberta Clippers, Colorado lows, Arklatex lows, Gulf lows, and the nor'easter or the Hatteras low. Now let me show you an example of this. Here we have a forecast. Now this was back on February 24th, 2017. Now what I want you to see is that right here is where the low pressure center was located. To the south of it, the cold front stretched right down here. And see this? This is all thunderstorms as forecast by the model. To the east, heavy, heavy rain. Right in through here, we were watching for sleet and freezing rain. And on the backside of the system, it was all about the snow. The storm system started in Colorado, went racing over towards Chicago. So this is definitely a Colorado low. We had all the warm air in this sector, the really cold air wrapping around the backside, and the cool air coming in just like that. So this is everything. This is it. Now, when it happened, look at what weather.gov issued. You see this map, they color code by county the risk. Follow the track of the low and see if what I just taught you made sense. So it goes right in through here. All of this, flood watches, flood warnings. All of this was actually a red flag warning. Remember I said dry air comes in the backside of these things? This was a red flag warning. That's a warning for high fire risk. On the northern side, the blues, actually just trace it all out right in through here. This is a winter storm watch. The pink is a winter storm warning. And the reds, in this case, were a blizzard warning. You see, it does it all. Severe storms to the south and flooding. Sleet, freezing rain, blizzards on the north and northwest side. It's all about the track. Do not forget this slide. That's a major, major take-home point of everything I want you to know about these things. And just like I said, to the south of the track of the low, there's severe weather. So by the time the low got into Michigan, so the low was sitting here, it draped a cold front just to the south like this. And all along that front, we were lifting warm, moist, unstable air, and they were projecting the development of a nasty line of severe thunderstorms right in through here. So here you go. This is a Storm Prediction Center map. North side, winter weather. South side, storms, rain. It's all there. It's the parent circulation for all these major types of weather. Now, oftentimes on the back side of one of these massive, massive low-pressure systems, we get colder outbreaks. And this one was very important from 2017. Now, I want you to first focus on the map that's in the upper left. Now, this is a map that comes out from the National Phenology Network. It's a spring leaf index anomaly. Now, what does it mean? Basically, what you're looking at here is a deviation from normal. Wherever you see the reds, that indicates that spring is progressing faster than normal. So we actually had a very, very early spring in 2017. If it would have been blues, it would have been a late spring. Now, why I'm showing you this is that throughout much of spring 2018, our jet stream went like this. Where there was a big ridge over the eastern part of the country and a trough over the west, okay? Now, you know this. Ridges are where you get your warmth. And that's why we were having a very, very warm spring. Incidentally, the groundhog predicted very cold spring that year, so that's why we don't trust the groundhog. Where we have troughs, it's cool, so I'll put a big C up here to say cool. So warm under the ridge, cold under the trough. Now, in mid-March, the whole thing shifted, and we got this over here. Do you see the ridge built out west and a deep trough plunged over the eastern part of the United States? The cold air in this trough, see how the flow dips to the south? The cold air in this trough came all the way from Siberia. That's cross-polar flow. And when that trough came through, it disrupted this very early growing season. In other words, we had crops coming out very, very early, especially a citrus crop. And in the southeastern United States, do you see this little icon right here? There was a 3-day-long frost and freeze event that destroyed over $2 billion worth of citrus fruits. You see, that's why it's so important to understand how the jet stream interacts with these big low pressure systems. So, just a neat example here. If we keep going, let me show you this. This past winter, this will be winter of 2018, on January 4th, or January 3rd and 4th, 2018, we had a massive low pressure system that was erupting right here, basically a Hatteras low or a nor'easter. There it goes. When you looked at its winds, look at how rapidly they circulated here. Now, a new term seemed to hit the news when this happened because meteorologists, well, we call these types of systems bomb cyclones. We call them that because the air pressure at the center of the low pressure system is dropping at a rate of 1 millibar per hour. Now, will you physically feel a change in pressure of 1 millibar per hour? No, but that is an enormously quick rate at which to drop pressure. So when that term hit the news, oh, everyone's like, oh, we're having a bomb cyclone, it's just exploding. Well, bomb cyclone just tells us the rate at which the pressure is dropping in the center of the cyclone. That term was first used in an October 1980 publication, so it was nothing new. But the media got a hold of it, and pardon the pun here, but it blew up, okay? So powerful, powerful Hatteras low. Now, what I want to show you next, there we go. What I want to show you next is what you can learn if you decide to continue to take courses in atmospheric sciences, because we're not going to get this deep in a 100-level course. But you see this map here? December 7th, 2016. This is how I like to interpret the weather. We're looking at the mid-level flow of the atmosphere, and there are troughs and ridges all over the place. Now, what I'll teach you if you decide to take future courses is how and why deep low pressure systems, like the ones we've been talking about, form. In Atmos 120, we're going to skip it. But check this out. Troughs and ridges. You know they're synonymous? Well, troughs are synonymous with cold weather and ridges with warm. And the jet stream flows between them. And what I teach my students in my upper level classes is how to pay attention to the pattern of the jet stream, to understand how, well, warm air advects or moves into a ridge and cold air dips into trough. See this? Look, wherever there's a ridge, it's warmer than average, hence the red color. Wherever there's a trough, it's cooler than average. You see, we learn how this pattern works because this influences everything. In the summer, it has everything to do with the way we grow our crops, with the amount of energy that we use to heat and cool our homes. In winter, well, the natural gas market fluctuates daily based upon stuff like this. And the big thing we try to understand is, why do low pressure systems explode into the atmosphere between troughs and ridges? Now, we're not going to dig into this too deeply in this class, but I'm going to tell you, we really dig deep into how this works. We understand the three-dimensional flow of the atmosphere. We learn about the continuity equation and how it applies to the atmosphere. And we do that so that we can understand how motions in the atmosphere and equations of balance help us determine where we're going to get air to converge and diverge. Where air mass builds up, the pressure increases. Where it drops off, it decreases. And that forces air to rise and sink. And it does so across 9 kilometers of depth in the atmosphere. Air goes up and down and sideways and spirals. It converges, diverges, and produces these massive low pressure systems that I teach my students how to diagnose and how to understand these maps and use them to predict exactly where these powerful winter storms that disrupt our livelihoods will form. And we do that so we can really understand why the atmosphere makes high and low pressure systems. Because ultimately, if you haven't noticed this yet, every single weather event I've taught you about is all about a change in pressure. And where do changes in pressure come from? Changes in temperature. And where do changes in temperature come from? They come from a planet that is round, that is beat on daily by a star that's nearby. and the equator gets more energy than the polar regions. And the disruption of heat across this planet, forcing the heat from the equator toward the poles, gives rise to these massive, massive systems. It's a beautiful, beautiful design that gives us weather. But what we have to learn about now is, how do these massive low pressure systems and where they track impact your livelihood? And that's the context of our lectures on winter storms.